infrared spectroscopy. We will learn about IR spectroscopy, which is actually also called as vibrational spectroscopy. Why? Because the vibrations are responsible for this type of technique. Now, when we say IR spectroscopy, we definitely mean that we are using a part of electromagnetic radiation that is called as infrared. And this infrared is a very small portion of the huge EMR which lies between the UV visible and microwave. But it expands through a huge wave number ranging from 13,000 to 10 centimeter inwards. Now, the IR radiation that is used in this type of spectroscopy, that is the IR spectroscopy, it actually helps to determine as to what functional groups are present in a certain compound. Like, for example, I have an unknown substance and I don't know as to what is its nature, what are its properties, and what groups are present in that particular compound. Okay, so I can take the help of IR spectroscopy, which tells me, okay, that such and such functional groups are present in my substance, which is unknown to me. And when I have come to know about the functional groups that are present in my substance, definitely I can predict the properties and the nature of that substance. Okay, and along with the information regarding the functional groups present in the substance, the IR spectroscopy is also helpful to determine whether the impurities are present with the substance or not. Okay, so what impurities are present? Actually, that can also be determined by using the IR spectroscopy. Now, let's see how does it goes. The IR spectroscopy definitely uses the infrared part of the radiation, and this infrared part of the radiation of the EMR is actually a very small portion of the huge EMR, but nonetheless it is still divided into three sections. First is near IR, which extends from 12,500 to 4,000 centimeter inverse wave number. The second part is the mid IR region, which extends from 4,000 to 400 centimeter inverse, and the third part is followed by far IR region that extends from 200 to 10 centimeter inverse as wave number. But out of these three sections, it is the mid IR or the middle IR region which is most commonly used by the analytical scientists, the organic scientists, and also in pharmaceuticals also we take the help of this technique. This is why, because actually the molecules, they absorb the radiation in this portion to induce the vibrational excitation of their functional groups, which are present in the molecule. Now, once we have mentioned that vibrational excitation of the functional groups is there, let's try to understand as to what this technical term refers to. For that sake, we need to learn the basic principle of IR spectroscopy. Means, what are those pillars on which this technique is based upon? Okay, now, to understand the basic principle of IR spectroscopy, we have taken the example of a very simple molecule which consists of chlorine atom and hydrogen atom, represented by the green and the gray sphere respectively. Now, the bond between the chlorine and hydrogen we have represented here with the help of a spring, a small spring, which is representing actually the chemical bond present between the hydrogen and chlorine. Now, why we have taken so? Let's try to understand. In any molecule, actually, the atoms, they do not remain in their fixed positions, but instead they vibrate back and forth. So, the atoms, they are not fixed in their positions, but they are moving. And how are they moving? They are actually vibrating in their position. Okay, now this figure will tell us how does that happen. See, the atom moves in, out, in, out. What is it happening? What action is taking place? The atoms, they are vibrating in their own position. Here I have reflected only one atom which is vibrating. Okay. Now, when the atom is moving back and forth, the bond which is connecting these two atoms, actually it will undergo a slight change. I hope all of you agree to it. Why? Because when the atom is moving back and forth, definitely it means that the bond connecting these two atoms together is not a rigid structure. Okay, So when it moves inside to the right, the bond length decreases, or let's say the length of the spring connecting these two atoms, it decreases. When the atom comes back to its position, equilibrium state, the length again comes back to its original equilibrium state. That means the shortening and the lengthening of this piece of spring is taking place. That is what is happening in a molecule, right? That is why we had just chosen up the spring to represent the chemical bond over here. Why? Because the spring could well make us understand the nature of the chemical bond. Okay, so when this atom is vibrating back and forth, a slight change in the bond length is taking place. One time it decreases, the other time it increases, or let's say come back to its original position. That is why the technical term of bond length, which we had been learning up till now, it actually gives us the average value of the length of the bond between any of the two respective atoms. In other words, the definite fixed value of the bond length that we had been learning up till our lower classes now is actually an average value. It is not a fixed value but an average value. Why an average value? Because it keeps on decreasing and changing time and again. Why? Because the atoms are vibrating in their own position. Okay, now such type of movement of the atom back and forth in a molecule, as you can see here, one time it elongates the spring or it elongates the bond, and the other time it compresses it. So it just happens to be appearing as if somebody is pulling out the spring and then releasing it, pulling out the spring and then releasing it. So it's that type of motion of vibration. It is called as stretching mode of vibration, which is represented with the help of a triatomic molecule over here, wherein the red spheres, they represent the two atoms bonded to the central atom, shown with the gray colored, dark gray colored sphere. And these atoms are actually bonded to the central atom by means of a chemical bond, which is represented by a solid green line over here. Okay, so the double-headed arrow here actually depicts the movement, the direction of motion of the atoms. In other words, it depicts the direction of vibration of the atoms, wherein the atoms move to the right and then to the left, to the right, to the left. Means one time the spring is getting released, the other time it is getting compressed. So likewise, the chemical bond is coming back to its original length and then getting compressed, coming back to the original length, equilibrium state, and then coming back, getting compressed. So such type of motion appears as if a spring is being stretched up and then released, and hence it is called as stretching mode of vibration. Right. Now, this stretching mode of vibration is actually categorized into two types. Now, how do we categorize them actually depends upon their motion, the direction of motion. Let's have a look. For that sake, we need to understand that the ring spheres over here represent the central atom, to which the blue colored spheres or the balls have been attached, or the atoms attached to the central atom, and the chemical bond binding these respective atoms is shown by the black line over here. So when these two atoms, they pull out simultaneously, they pull away simultaneously from the central atom, and then they come towards the central atom simultaneously, all together one. Okay, that is called as symmetric stretching. In other words, symmetrically, actually the bonds are lengthening and then compressing. Both the bonds are getting lengthened up simultaneously and getting compressed simultaneously, right? So that is called as symmetric stretching. On the other hand, when one of the bond disobeys the movement of the other bond, or let's say when one bond moves in the reverse direction to that of the other bond, that is called as antisymmetric stretching. Like for example, this figure represents the antisymmetric or the asymmetric stretching motion. What is happening? This atom is approaching towards the central atom, so the compression of the bond length is taking place. At the same time, the other atom, it is moving away from the central atom, so an elongation of the bond length is taking place. The very next moment, the reverse situation will arise. This atom will try to approach the central atom and this one will move away. So what is happening over here? The bonds they are not moving symmetrically. Or let's say the atoms, actually we should say, they are not moving symmetrically. Okay, they move one after the other, and that type of motion, it is called as antisymmetric or asymmetric motion, or the asymmetric stretching movement in an atom. Now in this type of mode of vibration, we see that actually a temporary change in the bond length has taken place. Okay, now let's come to another type of motion that is called as bending mode of vibration. Now, contrary to the stretching mode of vibration, the bending mode of vibration actually involves the upward and downward movement of the atoms with their respective bonds. So when the bonds are moving up and down, what is happening? The bond length is not changing. It is the bond angle which is going to change this time. Okay, so that is called as bending mode of vibration. So the bonds, they simply bend towards one another and then away from one another. Right. Now, depending upon the plane in which the three atoms lie with respect to the central atom, the bending mode of vibration can be categorized into two types. First is in-plane bending. Now, in-plane means the plane with respect to the central atom. Right. So when all the three atoms, they lie in the same plane, their movement lie in the same plane, it is called as in-plane bending mode of vibration. Now in-plane can also be categorized into two sections depending upon the direction of movement of the atoms. Now how does that go? Let's try to understand. For the scissoring mode of vibration, it's very easy to understand. You just try to imagine that you hold a piece of scissor in your hand. So when you try to cut a piece of paper with that scissor, what is the direction of motion of your fingers and thumb? You will slowly realize that one time the thumb and the finger, they move towards each other and then they move away from each other. They move towards each other and then away from each other. So what is happening over here? That motion, the direction of the atoms, they are one time moving towards each other and then away from each other. That motion, it is called as the scissoring type of vibration of atoms. Okay, so when the three atoms, they lie in the same plane, it is called as in-plane scissoring type of motion that we have just mentioned. Another one is the in-plane rocking. For rocking, again, it's very easy to understand. You just try to imagine that you're having some background music going on, right? And you simply want to enjoy the music. What do? The first thing that comes to your mind, you raise up your hands and you start waving your hands. Means you're rocking to the tune of the music. So how does that happen? Both of your arms, once they go left, the other they go right. So the arms are synchronized with one another. They're moving in the same direction simultaneously. So that is called as the rocking motion. Okay, for atoms also, when the two atoms, they move in one direction and then they move in the other direction together, then the motion, it is called as rocking type of vibration. And since they lie in the same plane as that of the central atom, it is called as in-plane rocking mode of vibration. Another type of bending mode of vibration is the out of plane. Okay, out of plane, again with reference to the plane of the central atom. Now when the those two atoms attached to the central atom, they are moving in the same plane, okay, simultaneously, and then moving out of the plane simultaneously, means they are synchronized with one another. Once they move in the plane and then they move out of the plane. Okay, so when they do it simultaneously, that is called as wagging type of motion, and it is out of plane wagging, right? Another one is out of plane twisting, wherein one atom moves out of the plane and at the same time the other one lies in the same plane as that of the central atom. The next situation gets reversed. Now this atom will move out of the plane of the central atom and the other one will remain in the same plane as that of the central atom. And such type of motion, it is called as out of plane twisting mode of vibration. So the vibrational transition has taken place, right? Means the moment, let's try to imagine that the molecule is possessing these types of vibration. Now such a molecule has been given the IR radiation, or the IR radiation has been subjected upon it. What will happen? The molecule will absorb the radiation, means it will absorb the energy of the radiation. The moment it absorbs the energy of the radiation, now what will happen? It will gain some energy. it will gain the energy from the IR radiation and now will start vibrating with a higher amplitude. Right. So this is basically what is happening when a molecule which is undergoing the stretching and the bending mode of vibration is subjected to the IR radiation. So in other words, the energy of the IR radiation gets transferred to the molecule, and the molecule now has larger amount of energy as compared to the initial energy, and now so it will start vibrating with a higher amplitude. This is called as energy transition. So actually what is happening in the IR spectroscopic technique, what are we taking advantage of? We are taking advantage of the property that whenever a molecule is subjected to the IR radiation, it absorbs the energy and undergoes energy transition. What energy transition? The vibrational energy transition. So this is called as vibrational transition, which is actually the basic principle of IR spectroscopy. So up till now we have learned that the different functional groups, they can stretch, they bend, they wag at different frequencies, and when they do so and IR radiation is subjected to such molecules, they absorb the IR radiation, okay, and then start vibrating with a higher amplitude. Right. So this is the basic principle of IR spectroscopy. Now let us try to understand as to what is an IR spectrum and how it is obtained. Right. For that we need to know that a particular molecule is undergoing stretching or bending mode of vibration, which we have just discussed. Now I have taken the example of the simple molecule of formaldehyde, which is having the molecular formula of HCHO. In this molecule there is a functional group present, which is actually the carbonyl group, that is carbon double bonded to oxygen. Okay, now I take this sample of formaldehyde and I put it into the instrument that is called as IR spectrometer. Right. Now when I have put this sample of formaldehyde solution actually, which is functioning as a sample over there in the instrument of IR spectrometer, I need to know certain features of this molecule that I have lately discussed. First is the carbonyl group is the functional group which is present in this molecule, right? And it is undergoing, let's say it is vibrating with 10 Hertz frequency. Right. So the stretching mode of vibration which the molecule with the functional group is showing over here is, let us say, it is 10 Hertz. Although it shows a very high value of vibration frequency, but for the sake of convenience we have taken a lower value, a simple value over here. Right. Okay. So the stretching frequency of the carbonyl group here is 10 Hertz. Along with this stretching frequency, let's say it also shows the wagging frequency of 4 Hertz, means it is showing the wagging motion with the frequency of 4 Hertz. Now this molecule has been put into the sample holder of IR spectrometer. Now if you remember, in the previous videos we had learned about the basic instrumentation of all the spectroscopic techniques, or let's say the spectrometers. Okay, so in that instrumentation, if you remember, the first thing that is present, the first part of the instrumentation is the source of light. Right. So here the sample is in the sample holder and I subject the source of light over here. From this source of light, the IR radiation is moving out, and which is then passing through the sample holder, which is actually holding my sample of formaldehyde. Okay. Now the IR radiation is made incident upon this sample. Now let us see what might happen. Suppose the frequency of IR radiation is, let's say, 5 Hertz. So what happens? The frequency of the IR radiation is 5 Hertz when it comes across the molecule, when it comes across the carbonyl group of formaldehyde, it sees whether it is matching with the frequency of carbonyl group or not. Frequency means frequency of vibration. Right. Now how will we come to know about this? On the other side of the sample holder, we get a part of the spectrometer, which is the detector, and this is the detector which has been represented with the vertical bar over here. Right. Now what does the detector says? When the 5 Hertz frequency radiation is made incident, IR radiation in fact is made incident on the formaldehyde molecule, the detector says, okay, it can perceive that some radiation has passed through the molecule and has reached the detector almost 100%. What does that convey to us? This simply means that the molecule actually did not bother about this radiation and it let it pass through it to reach the detector. In other words, when the IR radiation with frequency 5 Hz reaches the carbonyl group of formaldehyde, which is having actually the stretching vibration of 10 Hz, it is not absorbed by this functional group and it goes unabsorbed, and that means totally transmitted to reach the detector. Okay, now let us do one thing. Let us change the frequency now. So what do? I now subject a 10 Hz IR radiation upon this molecule, upon the sample. Now the moment the 10 Hz frequency radiation reaches the molecule, then what happens? What does the detector says? The detector says that okay, it could not perceive any of the radiation coming from the molecule, or let's say passing through the molecule, or it can be the case that only a meager amount or negligible amount, or let's say a very, very small amount of radiation is able to reach the detector through the molecule. What does this mean? It means that most of the radiation that has been passed through the molecule has been absorbed by the molecule, and therefore only a very little amount, let's say a negligible amount of it could be transmitted through the molecule. So we conclude from this that if the radiation which is subjected upon the molecule, it is having a frequency equal to the frequency of vibration of the functional group over here, or the frequency of the vibration of the group over here, then the molecule absorbs that radiation. Otherwise, it does not absorb the radiation and it transmits all the radiation. That means no absorption of the IR radiation will take place if the frequency of that radiation does not match with the frequency of vibration of the molecule. Okay, so when such a frequency has been made incident on the formaldehyde molecule, the other side of detector shows a spectrum like this. Right, now you can see the inverted peaks over here, okay, the dip which can be seen over here. This is how an IR spectrum looks like. We'll discuss it in our next slide in detail, right? And the IR spectrum of formaldehyde, actually the bands, they signify the CH stretching bands, okay, as well as the bending bands of the formaldehyde molecule. Moreover, we were just focusing upon the carbonyl group. So the carbonyl group over here in this spectrum, you can see a dip is obtained over here, right, at the wave number of 1750 centimeter inverse. So this basically dip which we obtain at 1750 centimeter inverse is due to the stretching mode of vibration of the carbonyl group, right? So this is how basically an IR spectrometer functions, okay, and this is how the molecule is detected using IR radiation and clubbed with the spectrometer, and the result that we obtain is in the form of this particular spectrum. This is called as spectrum. So this is how we get an IR spectrum from the instrument of our substance. Okay, so up till now what we have gained? Firstly, the functional group will absorb the light if and only if the frequency of the light matches the frequency of its vibrations, which is actually the stretching, bending or the wagging modes of vibrations. Right, and the second achievement that we get from here is that the IR spectra shows absorption bands that enable us to determine if a certain functional group is present in a molecule or not, or rather to investigate what is the functional group present in my unknown substance. Right, so after achieving these 2 points from the discussion so far, we then move forward, coming to another landmark, which is actually the eligibility criteria of any molecule to be studied using an IR spectrometer or IR spectroscopy technique. Okay, in other words, let us now try to understand as to what is the fundamental requirement for IR spectroscopy. What all molecules can be studied by this technique, otherwise they cannot be studied by this technique, and we need to know as to our substance can be studied by the technique or not, otherwise it will be just simply a wastage of time. Okay, for that sake, let's start with homonuclear molecules. Homonuclear, homo means similar, right? So when a molecule consists of similar atoms bonded together, it forms a homonuclear molecule. Very simple to understand. Like for example, we have hydrogen H2. It consists of two atoms of hydrogen bonded together with each other, right? Chlorine, nitrogen, and so on and so forth. They are the homonuclear molecules. Now, when similar molecules have been, the similar atoms have been bonded together by means of a chemical bond, then the question of having an electronegativity difference between the two atoms nullifies, right? Fine. In other words, we can say just because the similar molecules are bonded together, so that means there is no electronegativity difference between the two atoms. If similar atoms are bonded together, right? So there is no electronegativity difference between the two atoms. And when there is no electronegativity difference, that means there is no dipole moment, right? So such molecules, that is such homonuclear molecules, they do not have a dipole moment. And when a molecule does not have a dipole moment, it cannot absorb in the IR radiation to excite the bond vibration, right? So, in other words, a molecule is supposed to have some value of the dipole moment so that it can undergo bond excitation. Then only it will absorb the IR radiation. Otherwise, if it does not have any dipole moment, that means no absorption of IR radiation will take place, right? And such substances which do not possess a dipole moment and hence cannot absorb the IR radiation, they are called as infrared inactive substances or molecules, right? So we call them as IR inactive molecules, right, which cannot absorb the IR radiation, or in other words, which do not show an excitation in the bond vibration, okay, due to the absorption of IR radiation. Although there is no need to get disheartened over here. Why? Because such molecules can be studied by using some other technique, that is Raman spectroscopy, and we shall be discussing this spectroscopic technique also in our forthcoming videos, right? Okay, so let's come back to the topic. The second type of molecule is the heteronuclear molecule. Now, as the name suggests, hetero means dissimilar. Okay, so such molecules are made up of dissimilar atoms. For example, H and Cl, hydrogen and chlorine. Okay, CO, carbon and oxygen, iodine and chlorine bonded together by means of chemical bonds. All these molecules and such similar molecules, they are made up of dissimilar atoms. Now, when dissimilar atoms are bonded together by means of chemical bonds, definitely there is going to be some difference in electronegativity, right? Because the two atoms are not similar. Fine. So when such diatomic molecules are composed of dissimilar atoms, they possess a difference in electronegativity, due to which there will be some value of the dipole moment. So such type of molecules, they possess dipole due to the uneven distribution of electron around each atom. Why? Because the atom which is more electronegative, obviously it will try to attract the other electron also towards itself, and hence there will be an uneven distribution of electrons upon the two atoms, due to which a dipole is present. Now, when the dipole is present, actually the bond vibrations, they change the distance. Okay, so the bond vibrations, they change the distance, and hence the dipole oscillates. And when the dipole oscillates, that means when this entire structure is oscillating, a dipole structure is oscillating, this creates an oscillating electric field. Why? Because it is having charge. Partial polarity is present upon the respective atoms. Right. Now, this creates an oscillating electric field, which then matches with the electric field of the electromagnetic radiation subjected upon the molecule. And this is how the absorption further goes on. Absorption of the radiation. right? So that means a dipole presence is necessary.